Welcome to Study Time, a televised home learning program produced by Rwanda Education Board.
Hello, welcome again into this TV lesson learning program. My name is teacher Jean-Marie. I hope you still remember me. And we are together with the senior six. Senior six. I hope you remember the last lesson. So for the last lesson, we were discussing on the nuclear fission. Do you remember that? I hope you've tried to work on some other questions about the lesson. But now, I want you to have, again, the periodic table. Do you have them? You are ready with them. So, and I want you to have a calculator also. So because there will be something to calculate. Okay? And today's lesson is, again, a continuation of this nuclear reaction, but nuclear fusion, not fission. Okay? So, and we have the objectives of this lesson. I want you to be able, by the end of this lesson, I wish you could be able to explain or to define the nuclear fusion. That is one. Two, to calculate the mass defect from the reaction to find the energy raised, right? And I want you also to be able to give the advantages and the disadvantages of the nuclear fusion. Okay? So I hope that you are ready to have all of these objectives well done and well gained. So welcome again now. So I want to start with a very short video there. So let's play this. It is a very short one, okay? So that is a short video. Do you see that? So try to observe that again. We have this, and then it ends saying that we have nuclear fusion. Straight. Watch it again. So we have that, and then it ends there. We have nuclear fusion. I want you now to try and to define this nuclear fusion, to describe it according to the video, according to what you saw. Okay? So, my first question here is, what do you understand? Understand by nuclear fusion? And of course, you can refer to the video, just to the animation that we have there. So you can refer to that animation and then try to define that. So I'm playing this again, and then you tell me. There is something that is coming now together, and then we have that word done. Nuclear, then fusion. It means that for this one, you can now define it as having something or having two things that are combined. So when this is said, when two just two things combine, just are combined to form only just one one object. Let's say that is one object. So you can now say this according to the video. Did you think in the same way as me? Yes? Students, I hope you did that. Then let's have this continuation. We have the definitions. Definition number 1, nuclear. Do you know what it means? That's good. It means the process which involves the nucleus. And that's correct, students. And every time that you hear teachers saying you have nuclear physics, think about the things that are taking place in the nucleus. What involves this nucleus. Okay? So then we have fusion, means two or more entities coming together or emerging together to form one single entity. And I hope you see how it is matching with what you have given. And if you have given this one, and you are correct with the definition of that or with an explanation of this nuclear fission, but from the video. But now, the definition of this nuclear fission, because we have to involve the nuclear, the nuclide, the atoms, we have now to change it a little bit, but not going away from what we are thinking. So it is like adding here, so where you are saying the things, you are going out to add what? Then it is true. You are going to add atoms. You are going to add nuclei. Do you understand? The nuclide. So then you have the nuclei, two, and then to form one nucleus, but that is going to be heavy, according to what we have there. Now we have a definition there. It is, this is a light unstable nuclide can be combined to produce energy in a process called nuclear fusion. So I hope you remember this. You remember this from the graph that we used to that we use now to always give. There is a graph that I want you to be able to describe here. We have that graph. I'm not taking just much time here. We have energy. And this energy is what we call the binding energy per, that's true, per neutron. And here we have the number of neutrons. And then you have here, this is where the last time you had this uranium-235. But now, this time there is going to be the combination of these like atoms here, and to give another atom that is going out to be at that level. Okay? So it means that the atom being produced to be here. So this one is having an energy that we can now call, let's say the energy here is, let's say this is E1, this is E2, this is E3. So then you see that E3 here will now be just much bigger than what we have here as E2, and this E3 bigger than E1. Then we have this one is more stable, is heavier, or is having just a big mass than what we have combined. Do you understand that one now? So then, students, here we can now say what do you understand by nuclear fusion, as what I've asked you. This nuclear fusion involves two right nuclei combining to form a heavier one, together with the energy and one or more neutrons. So it is the same as to what we have said here, but what we have now to include into this definition, we have just to think about the nuclei and then to form a nucleus. Do you understand? So this time now, if you remember the diagram that we have given here, so we have the binding energy per nucleon here, so, and then this is the number of nucleon. So this time, if you have the energy as what we have, this is E1, this is E1, here this is E2. Then we find E3 is greater than E2 when E3 is what we have right here. So, okay? So, and also E3 greater than E1. You understand, the students? So this diagram can help you now to find out that the atoms, all of the atoms that we have by this side, we have them undergo the fusion processes. But the ones of this side, they undergo the fission processes, right? So I hope you don't have now to confuse this diagram with the one that just that we have added. The one that I said is an N, Z graph, whereby you have this line, of course we have another. So for these ones, we were only explaining the elements of this side, how they emit different particles from the ones that we have by this side, and the ones below, above 83, they decay by emitting alpha particle. So then, when we have our fusion process there, so it is the process which produces in the sun. Students, if you are being asked to explain where these fusion processes take place, please, where the fusion process takes place, you have to give the answer by saying that it is into the sun, or just the stars in general. That is stars. And then you are just correct with the answer here. Do you understand that? Please remember when you are being asked now to explain where. Yeah, you are asking yourself for now where we can have this fission taking place. That's good. The answer that you can give is this one takes place into the nuclear reactor, nuclear reactors. Okay? So so let's say while the fission process takes place. This is takes place into the nuclear reactor. Nuclear reactors. So this is how now you can distinguish these two. Now what is next is this reaction example, or the nuclear reaction. One such reaction involves the fusion of deuterium, hydrogen 2, and tritium, that is hydrogen 3, this one. You see that? So here we have hydrogen 3, and this is nuclei to form helium nucleus in neutron and energy. Remember, this energy is much raised by this time or into this reaction. Now, students, I want you again to recall on what we came now to say. It is taking place into the sun. Remember, we always say that the sun, into the sun, this reaction takes place, and what we feel, or what comes to Earth, is the light and the heat. Do you understand that? For us, we don't experience these reactions. We don't even have them, we can't observe them taking place. It is in the core of the sun, whereby hydrogen and hydrogen combine with the just combine to form helium, to form this heavy nucleus. That is helium. Or again, you can say that into the sun, we have this fusion of hydrogen and hydrogen to form helium, but by the release of energy, as we are saying. The energy is what now is what we can feel on Earth here. You have talked about much on the sun in scenario 5, but it is okay in scenario 5, unit 14. Okay? So then, students, we have this is hydrogen 2 and hydrogen 3, and they are combining now to form this helium. So I think that here we have, so this time you have the reaction process. So this is helium, hydrogen 2, combining with the hydrogen 3 to give helium. That is helium 4. This is together with a neutron. This is a neutron and the energy, right? So energy you can add on it or you cannot add, but you have into your mind that there is an energy. So please, you check on that. Here you have 5, and this is 5. The reason why we are saying we have a neutron, because here there is 2, and there is 2, there is 0, right? That is a reaction that we have. And there are some other examples of the reaction. So when lighter nucleides emerge together in a process called fusion, energy is produced and mass is lost. We'll have now to see how we calculate the mass. And here we have the examples of this nuclear fusion. So then let's have the other more examples here. So this is more examples. And this is hydrogen, and fusing with the hydrogen to give hydrogen 2, and together with a positron and a neutrino. This is what we have. That is the first process. Remember, into the stars or the sun. And here, that deuterium, or that hydrogen 2 combined with hydrogen 1 to give helium 3. This is isotope of helium. And then the 2 isotope of helium combines that then now to give this heavy helium. This is helium 4, together with the hydrogen or 2 hydrogen. And then we have, these are the examples that you can understand. But the side here is what I want you now to focus on, this side here. So whereby you have this light combined to give you heavy. Or this light to combine to give the heavy one, which is of course the helium 4. So then let's have the energy released during the nuclear fission. How do you calculate the mass defect and the energy due to this mass? How? So I hope you all remember this. You remember how we calculate this mass defect, right? And if you remember that, mass defect is calculated from the mass of reactant, subtracting from the mass of product. This is mass of reactant minus mass of product, and then you have mass defect. And you take that mass defect times the speed of light in a vacuum to find the energy. So you remember this also. So then we can have an example. So this is an example, and then let's use it now to calculate that energy. I hope we are ready to have the objectives, the 2 objectives being done, right? So good. Now let's have this, we have from this example, okay, answer of the example. What is being given? We are being given Look, the reaction that we have is, do you think it is this one or another one? Look at it. It's because they are telling us in a nuclear fusion reaction, a nucleus of deuterium, that is hydrogen 2, coalesces with the tritium, nucleus hydrogen 3. A helium nucleus is formed together with another particle, Yeah, take this as something that can now be asked to you, and then you are able to give or to identify another particle formed and write an equation for the reaction. So this time, here's how you have to do. What is being said there, it is that hydrogen 2. Hydrogen 2, you have it like this. And these ones combine or emerges with the hydrogen 3. Do you see this? Good. And then this gives helium. And together with another particle. So this time it is not going out to be helium 3. So, but it's helium 4 and then 2 plus, that is N0, just a neutron. In other words, the particle that is being emitted, it is a neutron. A neutron is a particle that is emitted. Do you understand, students? Good. In other words, I want you to just to be able to understand even how another question may now come in a different way. Sometimes this question can come just as a way of asking you, or just you are given the question and you are going to identify the equation, but with the particles that are there, that are being asked. If we were asked now to also to show the energy, we would have now to add on that energy here. But no energy that was asked. Because if it was together with another particle and energy, we would have now to show this energy into the equation. So then let's have the answer to question number B, which is, of course, the one that is going to let us go into the objective. Here we have a combined mass of deuterium and tritium is that 5. So it means that this combination, here the mass, we have a mass of 5.0, that is 31 U. And then here there is a mass, the mass of 5.011 U, right? So let's have the subtraction as usual. So here we have the mass defect. The mass defect is going to be equals to 5.031 U minus 5.011 U. And then the mass defect here will be equal to, this is going now to be 0. Here we have U. So this is 0. And here when we subtract, we find 2. And then here we are having 0, right? And this here, it is going to be 0. And this is 0.2 as the mass defect. Then let's find, calculate the energy. Energy here will be equal to what? You know, 1 U equals to 1.6 times 10 power to negative 27 kilogram, right? We can find that, or what is there as C square is equal to 930 mega electrovolt. We have defined this constant per U, and then we have this energy equals to mass defect, right? C square, and this gives 0.02 U times 93 mega electrovolts per U, and then here you find. Can you calculate together with me? So let's do that. We have this is times 930, and this gives 18.6 mega electrovolts. This is the energy that is being released. Okay? So then let's have the advantages and disadvantages, right? So we have the advantage here, number 1. Fusion is more productive energy source than fission per kilogram of material. This is a good production of energy. But students, this one is not easy. It is very difficult to be done because it requires so much more other heat or temperature to be performed or to occur for this fusion to take place. Do you understand? And to manufacture a material that is going now to stand for this temperature, it is not easy, right? That's why. And then we have the raw materials for fusion can be obtained from seawater. And here we have the waste products are not radioactive. That is good. And then the last one is uncontrolled chain reaction cannot develop. Remember what we have said. We have said that the uncontrolled chain reaction into the fission process, when taking place, it is possible for you to to make. So this is what is enabling the scientists to develop these atomic bombs, right? And then we have the, let's have here a homework, right? The homework for you. A homework that I'm going to give you, I want you to take the pens and the paper, and then you write down this link. Here, you are going now to follow the link. Do you understand, students? You follow the link, copy this one as this. https://forms.gle/ and capital letter R. As it is up to you, finish. I'm letting you now to have a look. Have a look on it. And thank you very much. I hope you have gained all of these objectives from what we came to do into this lesson. And I thank you so much for having me today into this lesson. I hope that it was so beautiful for you not to fear about this nuclear physics. Okay, so I wish we will meet again into the next other lesson. Bye-bye.